Hello. In our last video, we assigned ourselves the noble task of determining if we set fire to one tree, what other trees will burn down. And of course, because society frowns on performing this experiment in an actual forest, we're performing it virtually. And we wrote a recursive method to determine that, but we didn't actually succeed yet. Let's do a quick recap of what we wrote. We said, if you try to set fire to something that's not green, well, then nothing burns, so we return that 0 trees burned. That was our base case. And otherwise, we try burning in the cell just above and to the left and to the right and below. And after those 4 recursive calls, we add up the 4 numbers we get back, plus 1 more for the originals for the cell that we clicked for the tree that we were setting fire to. So the total number of trees that burn are all the trees above, plus all the trees to the left, plus the right, plus below, plus this tree itself. And we learned that when we tried to set fire to 2 cells that were right next to each other like this, we found that we ended up with a stack overflow error that line 72 called 73 called 72, and those were the lines that set fire to the left and the right. And we realize now that means when we try to set fire to this cell, it makes a recursive call on the right, which makes a recursive call on the left, which makes a recursive call on the right, and the recursion never stops, so we need to get to a base case. And so there's a few things we need to do. One, we need to make sure we keep track of which trees burned. That was this note we wrote here. Keep track of which trees burned so that we don't try to burn them again. How do you keep track if a tree burns? You burn it. You change its color. So I know I can change the color of a tree in this fashion. Don't get too hung up on how exactly I'm writing this code in Java and how these classes work. The main thing is the recursive structure. Set color of the tree that's at this location to be burnt. What's a good burnt color? How about gray? And a good gray might be something like 100, 100, 100. Equal parts red, green, and blue, and not too bright, so that will be gray. So we'll set the color to be gray, and I happen to know that this isn't going to work too, but I want to show you it not working, because it's such fun seeing code not work. Here we go. There's my forest, and I go to set fire to it. Just try this cell in the middle rather, and it says 71 calls 74 calls 71 calls 74. It's another stack overflow, and here 71 is burning up, 74 is burning one spot below. So Java's going up then down then up then down then up then down. It's the same problem that we saw a moment ago, so we haven't fixed it by setting the color gray, and the reason is because we're setting it to be gray after the recursive call. So it doesn't matter what we do after the recursion. The infinite recursion happens up here. We need to make sure to mark the color before all of those recursive calls. And by the way, I should point out that by marking it gray, we've said there isn't a tree there, right? Our base case says if the color is not green. Well, gray is not green, so gray will be treated just like black, and the recursion will stop. Let's try this. I'm compiling. I am waiting. I'm calling my test burn for here. Okay, let's try. Burn. I don't know, what should we burn? How about this clump over here? Ooh! Oh, wow! It did return. It did turn gray. And how many trees did we just burn? 1, 2, 3, 4, 5. And 5 trees burned. It appears to be working. All right, let's try some more. 1 tree burned. 1. It's returning 1. Yes, it is. Wow, we're doing great. Maybe we should go for broke. Let's try this one. Ooh. It only got some of it, and then it crashed. Let's see if we can figure out why. So here's burn, calling burn, calling burn, calling burn, and then finally it says, the error message says, it can't get the color from an invalid location. And you can't see it's off the screen, but it tells me the invalid location is 10, -1, which I happen to know means row 10, column, oh, this is column 0, column -1 is off the screen to the left. It's trying to burn a tree that's off the screen to the left. No wonder it's crashing, and it's crashing when I try to get the color, and I apparently call getColor on line 68 of my recursion code. So here's line 68. When I go to get the color of this location, if it's green, my program crashes. Or sorry, excuse me. I get the color of this location. If that location is invalid, then my getColor method call fails, and we don't actually succeed in testing whether it's green. So apparently we have another base case. We have a base case of whether it's valid. So, and we might be tempted, we could do that in one line here. We could say, if it's not green and it is a valid location, we'll ask the grid if that's a valid location. And if you've worked with Booleans long enough, you remember short circuit Boolean, and this means that we're going to test this condition, and if it's true, we'll test the second condition, which is a problem because this first condition is what was crashing, and the second condition is what's going to keep us from crashing. So we need to test and make sure it's valid before we attempt to check that it's not green. So if it's not valid, that'll be false. False and anything is false, and we'll return 0. If it is a valid location, if it's within the boundaries of the grid, then we'll get the color of that location, discover perhaps that it's green or not, and do the right thing based on our code before. So let's see if that works. Compile, and it's happy. And we'll try running that again. Here we go. Let's burn some trees. All right. I'm going to set fire to this one. That's good. You know what? I'm going to move this so we can see the number appearing. 1 tree burned. Let's try here. 3 trees burned. That's good. How about if we click it again? Oh, 0. That makes sense. And 0 trees here. 1. Let's try one that's going to be near the edge of the screen. Ah, we didn't get it yet. We didn't get it. Who wrote this code? Let's see what it says. It says 73 calls 72, which calls to set color and tries to set the color of an invalid location. Huh. I thought we tested if it was valid. Ah, we had it backwards. You were supposed to be watching me. I'm sure you noticed that. If it's not valid, and it's... Sorry, I think we have that entirely backwards. Let's see. Alright, so if it's not valid, or it's not green, then it's no good. Then no trees burned. If it is valid, and it's green, then we will continue with this code. I think that makes much more sense now. I think this just serves to underscore just how important it is to think about our ands and our ors, because it's very, very easy to mess that up or to confuse the nots versus not nots. And you see, even your illustrious teacher here can confuse it. I apologize for that. Okay, if it's not valid or it's not green, then it's not a tree, and so nothing burns. Alright, let's try that again. It's going to work this time. I can feel it. There's my forest. We'll move this so that we can see how many trees are burning, and we'll click. 0 trees, that's good. 1 tree, nothing left. Once it's gray, we'll try another one. Ooh, look at that. Look at that. Oh, wow. Oh, this is what it's all about. Look at all those trees on fire. Yes, burn, 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 burn. Oh, this is the dream. All right, this is what computers were invented for. A couple things we might want to take a look at here. One, we can actually watch the trees burn, which is much more satisfying, by throwing in some weights. So I happen to have a wait for key press method, and if I call it, we can actually watch it burn. So after setting, whenever we change the color, we will call this little wait method I happen to have written. Don't worry about where it came from or how it works. And that's going to wait for, apparently it's going to wait for me to press a key. So let's try that out. Please burn the forest. There it is. So now it's waiting for me. So which way is it going to go? Well, we told it to go up, then left, then right, then down. So Java's going to try burning up. And then it's going to try burning up again, but there's nothing above. So the next one that will burn will be to the left. And then up, 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 left, up. And at this point, it's stuck. And so the recursion is going to back up. And where's it going to back up to? It's going to back up to here, where it's already gone up, and now try going left. And in fact, we can see that more clearly if we add some more colors, which is going to be kind of fun. So what if we set the color here, instead of gray, let's copy and paste these lines. I'll show you what I'm going to do with it in a moment. What if we set the color, let's put more of this on the screen, so that when we reach a tree, we will set it to be yellow. Let's see, that's, oh boy, yellow is all red, all green, no blue, I believe. It's yellow, so it will look like it's on fire. And then we'll wait, and at some point later, after all the recursive calls, we'll make it gray. to indicate that it's burned out, I guess. Let's see how that looks. Ah, this is fun. This is fun. We are playing, making colorful fires. Okay, let's try that. So there's the yellow. It's burning, 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 burning. And now you can see as that recursion comes back, as it unwinds, it turns gray. Okay, let's try another one. We'll burn here. So there's yellow. So it's going to go up. And now it can't go up or left, so it will go right. Now it will prefer up. It always goes up, then left, then right, then down. So it can't go up or left, it'll go right. Now it can go up. Now it can't go any of those directions, so it will backtrack to here, where it's gone up and left, but now it can go right. And now it's gone up and left, so it can go right. Now it can go up, up. Now it's stuck, so it will backtrack to the point where it can move again, and now it can go right, down, left, left, backtrack, down, 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 backtrack, backtrack, all the way over. Oh, that one burns. Now I think we're stuck. No, we're not. We're down here. Okay, fine. We're down here. Now we can go down, I think. And then left. And you can see all of those, all the recursion as it's filling in this region, backtracking. And I think that gets at actually why we care about this algorithm. No, we probably don't really want to burn down forests. Maybe that's not an interesting question. But an interesting question is, how do you fill a region with a particular color? Think about any paint program you've ever used. You click to fill it with paint. How does that work? Well, here's one way it could work. Here's one way where we could write recursive code to fill in a region of color. And if you think about it, a lot of video games you might play involve filling in a region in some way. So for example, if I play Super Puzzle Fighter 2 Turbo and I explode a gem, that gem is going to explode in some big contiguous region, and this is going to find that contiguous region is recursive code like this. Or maybe you play a game called Flood It, which uses this idea. Maybe you play Minesweeper, and whenever you click and you reach a 0, a cell that has no mines around it, all the Windows Minesweeper will recursively clear out all of those zeros. How does it clear out all those zeros and find that contiguous region of zeros? It uses this algorithm. So this is actually a very useful algorithm, and I think it's one of the first algorithms you might see where recursion that really makes the case for recursion. This is a relatively easy code to follow, although I realize we've gradually made a mess of it, but relatively easy code to follow that achieves something that seemingly sounds very difficult, which is how do you find and fill a contiguous region. Alright, thank you very much. I'll see you in the next video.